All right, let's get started. We're into our next session, and this is actually looking at applications to energy use and their emissions, which is a hot topic, particularly now when we're looking at fracking and such. And we'll do this just the same as we did before. We'll call up the speakers, and they'll come up and present, and then we'll wait for questions till the end, and then we're going to get the whole panel up here to answer the questions and to drive the discussion. So with that, the first person is Dan Goldberg, and take it away.
Thank you, Ted. Thank you all for coming. Thank you, online audience, for attending. So my title is there, Pushing the Boundaries of NOx Emission Quantification from Remote Sensing Instruments. And for all of my plots, I'm going to be using data from TROPOMI. On your left is the 4-year average of TROPOMI over the continental United States. And if we zoom into this general vicinity, we can see that the hot spot in this area is the Chicago metropolitan area, not a surprise. But what I did for this particular conference is I zoomed in to Madison. And I changed this color scale a little bit so you can really get the spatial gradients. And what I really like about this is you can see the downtown area. I don't know if people online can see, but we are located right here, right in the center of the worst NO2. And this spot right here is the airport. So it's amazing that TROPOMI, this is a 4-year average, can really pick up on these really fine details within a metropolitan area. So that's really what's driving this presentation and my work for HAQAST. All right, so before going any further, I really want to thank all the people that are contributing to this presentation as part of both our core project, but also the Tiger team listed there. Can't list everybody's name, but I will mention people when they've contributed specific images. So the motivation is the improved spatial resolution of TROPOMI. It now allows us to assemble information at the local scale, approximately 1 kilometer spatial resolution. So the questions are, can we use TROPOMI data to differentiate between NOx emission sources, highways, ports, airports, large point sources within a metropolitan area? I sort of answered that question already for Madison, but we'll take a look at a couple other cities. And can we use TROPOMI data to diagnose environmental justice issues within urban areas? I'll discuss that a little bit today, and Gage Kerr will discuss that a little bit tomorrow in his presentation. All right, so one thing that I've been doing is I've developed this website with help from students in our department. It's TROPOMI no2.us, and I just snapped this picture from earlier in this week. So on the left is the TROPOMI NO2 for that day. I believe that's Monday, if I do. Yeah, I think Monday. And then on the right is the difference between that image and a seasonal average of the fall. And so on the left, it's probably helpful for people in this room, but I think on the right is helpful for a lot of the stakeholders in this room, where we can very quickly convert this into a ratio. Is it higher or lower than normal in a typical day? And so what I like about this is you can see that generally it was actually a little bit below normal NO2 this week, which is good. Some exceptions kind of in the Pacific Northwest. And so this is just this week. But I actually did the same image comparing this past summer to 2018 and 2019 summers. And actually, so typically we would think that the NOx emissions are going to go down each year. EPA, that's what the EPA is projecting, but I'm not so sure that's actually the case. We can see that in several cities, that is the case. Some of the big cities, New York City, Chicago, San Francisco, et cetera, but kind of the center part of the country, we are not seeing a decrease in NO2. This is a more rural area, so there could be some other influences from background sources. I don't want to get into too much of the hypotheses. However, there are a lot of, let's see if this is going to work. Oh, this is working. This is actually, I did some research here. This is actually a really big gas field in southwestern Kansas. So we actually are perhaps seeing some increases in some of these areas that are due to more natural gas exploration. So that's, I think, kind of the next topic in the next coming years that with transitioning away from coal to natural gas in some of these areas that are really prolific with natural gas could become larger NO2 NOx emission sources and have larger NO2. Another thing that I've been doing recently is I've developed some tutorials on YouTube. You can go there. I put the tiny URL. I also, you can join our Tiger team, etc. Look at these slides later. You can go to these YouTube tutorials. Here's just a screenshot. I have, I think, 5 or 6 videos now describing what satellite NO2 is, but also how to download TROPOMI data. There's actually a lot of different ways to download TROPOMI data, and specifically which variables you want to look at when you download the data. It's a very, very large file, hundreds of megabytes, lots of different variables. So I was trying to give an explanation of that in that tutorial. So one thing that has been published since the last meeting is this paper in ACP, and I have a Twitter thread, you can follow that, but I'll give you a very quick synopsis here. The satellite and inventory in Texas cities generally agree pretty well with each other. Well, there's some exceptions, and I'll describe that in a second. So if you go to the bottom right, there might be a potential inventory underestimate for NOx in the ship channel, and then similar minor underestimate in downtown Dallas top, but there might be a potential inventory overestimate specifically at the Dallas-Fort Worth airport. So there's probably just some type of spatial misallocation in this particular example. But one thing that should pop up in all the examples are the satellite having a difficulty to estimate NOx emissions from large point sources. And actually I went to a conference last week, there's a geophysical reason for this, because the satellite pixel is about 5 by 5 kilometers, but the actual plume is on the order of tens of meters, sometimes hundreds of meters. So the satellite is just having a hard time picking up on it. So with finer spatial resolution, with satellite data, we can perhaps get beyond this and not have this satellite underestimate. But then there's also what Ted was discussing, the NOx to NO2 ratio. So one thing that we're doing specifically as part of the Tiger team is to compare TROPOMI NO2 during stagnant wind days to the NOx emissions inventory directly. And I really have to give big thanks to George Mason and Daniel Tong's group, who processed the national emissions inventory down to 1 kilometer spatial resolution. So what we're doing here is we're converting the TROPOMI data into percentiles within a metropolitan area. And then we're doing this same thing with the graded emissions inventory, and then comparing the two once they're in these essentially same units, which are percentiles within the metropolitan area, and seeing how well this compares for a variety of different metropolitan areas. So here I'm just showing 4 different metropolitan areas. And the first thing that you should definitely look at is the R squared. So the R squared is really high, which means that the national emissions inventory is spatially allocated pretty well if you're using TROPOMI as the truth. Whether it's the truth or not is a different story, but it's very nice that we're seeing very strong correlation in all 4 of these cities. In LA, I didn't show that the correlation is a little bit lower. So what we're actually trying to do is isolate some of these outliers, both the red outliers and the blue outliers. The red outliers would be a potential NOx inventory overestimate, or potentially the satellite's having difficulty observing the source, and the blue would be a potential NOx inventory underestimate, or sometimes this could be NO2 outflow from a nearby source. For example, if you had a big power plant next to an ocean or a lake area, the lake would have no emissions, but the power plant would. So sometimes you get those types of things with these blue points. So hopefully this will run. I did a nice little comparison here, showing the NOx emissions inventory to satellite data itself. I thought this was pretty cool, just sliding back and forth. I've made these for a bunch of different cities, but it's really nice that you can just do this nice little comparison between the two at that exact same spatial resolution. And I can discuss a little bit more about the intricacies of this plot in the discussion if there's interest. All right, so just looking at Chicago here as I wrap up the presentation, the NOx emissions inventory is on the left side, the satellite percentiles on the right side. And if you look at the northern part of Chicago, this is a very wealthy area. The emissions inventory may be overestimated. So when the emissions inventory, we're seeing not large, but moderate NOx emissions, and the satellite is seeing very little, or on from a percentile standpoint, less. And then on the southwest side, where there's actually a lot of warehouses, so this is prompting our rapid response project, which we discussed later, is that we can see that the emissions inventory is, say, moderate in this 50th percentile or so, but we're seeing 60th, 70th percentile in the satellite data. So that's suggesting that warehousing is perhaps not allocated appropriately in the NOx emissions inventory. And so that's going to be future work for our team and the rapid response team. So just some quick conclusions. Your real-time data, check it out. I think there could be a potential super recovery in some sections of cities. I didn't discuss it, but Ted showed a nice example in last session about the super recovery near ports, but also warehouses, which is what I showed today, potentially. And then under the right conditions, specifically long oversampling times, and also on days when low amounts of winds, we can sometimes compare the satellite data to NOx emissions. And generally, there's excellent spatial correlation between the two, but there are some remaining areas of improvement, such as near EJ communities or warehouses, ports, and industrial areas. So with that, I'll stop here. Thank you very much.
Thank you, Dan. Our next speaker is Monica Harkey from Madison, Wisconsin. Madison.
Okay. Hi, I'm from the Center for Sustainability in the Global Environment here at UW-Madison. This work has been sponsored by NASA HAQAST in partnership in collaboration with the Rocky Mountain Institute. I'm excited because no one except for the people whose names are on the screen have seen these data before, so they're very new. And it's a little bit timely. We've had some cold weather here lately, and whenever I turn the heat on for the first time in the fall, I get a song in my head. And maybe you're old enough to know that song. There's some jazzy stuff in the intro, and it goes, "The heat is on." So RMI was curious about building heating emissions. What happens when we turn on the heat? If you are using a fireplace, you may see stuff come out of the chimney. You may see steam coming out of a pipe if you have like a gas furnace, or you may not care or notice. But RMI was curious, what happens when stuff comes out from building heating, residential, commercial, industrial. And those of us at HAQAST were like, ooh, that's a great question. We can investigate that. So what do we know about emissions from buildings, from heating? Residential wood combustion, this is all from the 2017 NEI. Those emissions are based on a 2018 survey, and then they do some extrapolation, allocate based on minimum daily temperatures. So if it's colder, they assume more stuff is emitted into the air because people are burning more stuff. Natural gas heating is a little bit more simplistic. They take state level energy consumption. It gets allocated spatially based on census information, employment, housing, appliance type stuff. And then you get one representative week each month. So 1 week in January, that represents all of the emissions for January from building heating. 1 week in February, etc. So we want to know, can we use satellite data to improve this? But a bigger question to investigate first is, can satellites even see this? I mean, it's just building heating, right? Not cars. So what do we know about building heatings? According to the 2017 NEI, the fraction of building heating is shown in this map. And the top 10 counties with the highest percentage of building heating emissions compared to the total are shown here. Most of them are in the New York metropolitan area, with assorted counties in West Virginia, DC, Ohio, and Texas. So those emissions in the top 10 counties proportionally account for like 20 to 30% of their NOx emissions are from building heating. So that's interesting. Maybe that's going to be enough to have a signal in TROPOMI. We'll see. All right, what does satellite, what is TROPOMI seeing? It's seeing the full column. It's seeing all the emissions mixed together, all the chemistry that's happened, all the meteorology that's blown things around, sideways and up and down and all over the place. Keep that in mind. It's seeing sort of a windshield view. It's not a nice regular shape. So I use something called WIPS, the Wisconsin Horizontal Interpolation Program for Satellites, to transform that windshield view to a nice 4-kilometer regular grid, which I then allocated to counties. And this is what we see for 2019, the cold month average when we're looking at when there's heating. So January, February, March, November, December, 2019. And Ted had a nice point in the last session about how air quality has improved. And you may notice if you've been looking at satellite column amounts of NO2 for a while, we used to go up to a much higher number, like 30. And to get this to show up, I went to 10. So, you know, to get more detail in our maps, we have to scale things down. That's kind of cool. You can see that there are higher column amounts where there are more people, more combustion activities, cars, heating, you know, whatever else, especially in cities and also in industrial power plant areas and stuff. Okay, so that's what we see with satellites. Now, what about building heating? If you remember back to residential wood combustion, they allocated those emissions based on a daily minimum temperature. So they're using temperature, outdoor temperature as a proxy for those heating emissions. So what can we do? We can look at daily minimum temperature too. We can look at daily maximum temperature. Since we're comparing to TROPOMI, why not look at the temperature at the TROPOMI overpass? Or something that's used in building heating and energy. If you look at your utility bill, you might see cooling degree day and heating degree day, depending on the season, something called heating degree days. So I actually looked at the relationships among all these temperature metrics and TROPOMI NO2, and I found that the strongest relationship was with heating degree days. What are heating degree days? This is a nice map from the Climate Prediction Center showing the sum of heating degree days for all of 2019. It's calculated with a base of 65 degrees Fahrenheit, and the base can be different, but this is what we tend to use in the US. So if the daily average temperature is 35 degrees, and you want to know the heating degree days, you subtract that daily average from the base. So you have 30 heating degree days. If the daily average temperature is 55, you have a heating degree days of 10. And we generally see sums of these daily metrics on our heating bill or in a plot like this showing an annual total. You can see, as expected, northern latitudes, you have more heating degree days than in southern latitudes. So what is the relationship between TROPOMI NO2 as a proxy for building heating and these heating degree days? And I looked at those top 10 counties again: New York metro area, West Virginia, some parts, Ohio, DC, and Texas. Averaged over all those counties, heating degree days in the red, TROPOMI column amounts in the gray. We would expect that as heating degree days go up, there's colder temperatures, increased heating demand, that we'd see TROPOMI column amounts go up, and we see this positive relationship. And we do see a positive relationship, but it's not very strong. The correlation is low to moderate. And I would say, you know, there's a lot of confounding effects. There's all that meteorology, there's all that chemistry, and there are a lot of other emissions. You know, remember, building heating is less than a third of the total NOx emissions. And that's like for the highest building heating proportion county. So, all right, maybe we need to drill down to the county level. And here's the county level. Again, I have an overall picture here, heating degree days on the x-axis. You see there's a general positive relationship here, and the county level, each county here at the top. The green dots indicate whether that correlation is statistically significant with a p-value of less than 0.05. So for about half the counties, those relationships are statistically significant. generally for the higher correlations. But why is there so much variability among these counties? Is it because there are meteorological differences? Are there other emissions, maybe like traffic? Traffic is a really big source of NOx. I know some differences in West Virginia counties. Some of the West Virginia counties have major sources of employment are hospitals, really, really big hospitals, and that's where everybody goes. One of them has a cream cheese factory, so maybe that's a really big source of emissions. Who knows? We gotta look into this a little bit more. But one thing we can look into a little more easily is the effect of traffic. So let's look at weekday, weekend. We expect that on weekdays, more traffic, people aren't home as much, maybe their thermostats turned down if they're being responsible. Weekends, less traffic, people are home, heats up because they're there. So what do we see? Here we go. Weekdays, correlation is lower on average. Weekends, correlation is higher on average. Okay, that's kind of what I expected. And this holds true for most counties, but not all of them. A couple of them, the relationship actually degraded and they diverged. The correlations are negative. So that's something interesting that we would like to look into. Another thing we could look into are, what's the relationship between the change in column amount, TROPOMI NO2, and the change in heating degree days. So if it gets colder, we have a cold snap, are we going to see a corresponding increase in TROPOMI NO2 column amounts? And the overall correlation is less than half of what we saw for overall. So it's not a strong relationship, but again, it is a positive relationship. We see as it gets colder, TROPOMI NO2 column amounts tend to go up. How is this separate from meteorology? We need a model for that. But it is reassuring that Dan had a paper a couple of years ago that showed the other end of this, that as temperature increases, which would be as heating degree days go negative. Is that me or is that?
That was me.
Okay. As temperature increases, column amounts go down in the summer months up until a certain point, and that was hypothesized to be because of air conditioning demand, power plants firing up. So we do see some moderate increases in column amounts, not always statistically significant. So this is all very interesting, and we'd like to explore it some more. Back to my original question of can we even see this from space? Yeah, kind of. Considering that the signal from building heating is not a really strong one, I wouldn't say this is too bad. We see stronger correlations with column NO2 and heating degree days on weekends as expected. And some counties you see a better relationship than others. We'd like to explore that some more. And one big piece of that is, well, we just looked at 2019, add in more years of data. So that is ongoing right now. Another thing is heating degree days with a base of 65 Fahrenheit isn't really that great. Like it does, technically it should vary spatially. So what if we change that to fit the building stock and like the heating needs of different areas geographically? That would be something to look into. In the end, it would be great to see if the relationship between heating degree days and TROPOMI could be used to improve the temporal allocation of gas heating. So we don't just have one representative week. We actually have day-to-day variability. That would improve the modeling. And maybe TROPOMI NO2 can be used to improve spatial allocation, to work in tandem with the survey and census work that goes into building those emission inventories on the county scale or sub-county scale.
Thank you, Monica. Our next speaker is Jeff Jaeckels from Madison Gas and Electric.
All right, good afternoon, everyone. I'm going to be talking a little bit about the energy transition in response to global climate change and how your all work really supports what that energy transition does, and specifically methane monitoring, and how that plays a supporting role in this transition. So this is a different presentation than what you guys have all been doing. This is not an academic type presentation, but I have been asked to talk about, again, what you guys do and how it supports other areas. And there was actually a question regarding that in the last session, like, what do you guys think about what you do and how it impacts other areas? So that's what I'm here to talk about. So I'm the Director of Safety, Sustainability, and Environmental Affairs at Madison Gas and Electric. And I have the opportunity to help our company kind of identify technologies and work through setting goals, targets, and that sort of thing for the energy transition. And we're one small piece of that energy transition. So I'm talking a little bit more globally in this presentation. So real quick, this is the company. We have 159,000 electric customers and about the same gas customers, primarily in Wisconsin, southern Wisconsin. The UW is one of our biggest customers. So electricity, gas use that the university has here is supplied by MG&E. We also share a cogeneration facility on campus, on West Campus, which provides steam and electricity to campus and electricity to MG&E. So we're about 150 years old. We're known as your community energy company, and we have about 700 employees here in the area. And so this energy transition that I'm talking about is really in response to climate change. As I'm sure everyone here knows, climate science suggests that the global economy really needs to attain net zero greenhouse gas emissions by mid-century to avoid the worst impacts of climate change. We're already seeing impacts of climate change. And so the power sector really needs to lead, and particularly the electric power sector. And that's half of our business is the electric side of generation and distribution of electricity. And the reason for that, obviously, is that as we lower our carbon footprint within the carbon intensity of electricity, we can help electrify other areas of the economy, including transportation, and lower their impacts as well. So that's exactly what we've been doing on the electric side. We've been engaged in a energy transition since the early 2000s. We've been updating our goals fairly continuously. And right now where we're at is we do have a net zero by 2050 goal for our electric side of our business. We have an interim goal of 80% decarbonization by 2030. And we worked with the UW here to verify our trajectory against the IPCC science. And that was actually Tracy Holloway and her group who helped us. And as you as well, right? Yeah. And so I'm surprised to see that face all of a sudden. I mean, you did in the meetings at MG&E, and I just recognize you right now. So thanks for your work. So yeah, we have people in the audience here who helped us with our trajectory. The strategies that we have primarily are decarbonizing the grid. Obviously, we'll want to get as much carbon out of the intensity of the electricity as much as possible. We want to work with customers so that they use as little electricity as possible. And we want to electrify transportation and other sectors. The other side of the business is the natural gas sector decarbonization. And we're part of this, right? We're probably the bottom piece of this diagram. But the natural gas industry is huge, and it covers a lot of territory. There's the producing wells, there's the gathering stations and facilities, processing facilities, compressor stations. Natural gas is stored in underground caverns and is pumped in there during the warm months so that it can be taken out in the cold months. So natural gas is moved around quite a bit. It goes directly to some power stations. It goes to transmission pipelines and into distribution systems like ours here at Madison Gas and Electric. And then the natural gas eventually goes to burner tips, whether that's furnaces in our homes, whether it's a power plant or a gas stove or industry. If you talk about the emissions, greenhouse gas emissions from the natural gas industry, it's pretty much fugitive methane emissions from the wellheads to the burner tip, right? And in the burner tip, it's the CO2 that's combusted or is formed through the combustion of the methane. So this is currently a national focus, is trying to drive carbon out of the natural gas industry. And right now the focus is looking at, if you look at the end use emissions, looking at emission reductions, energy efficiency, electrification to, again, substitute those furnaces with maybe heat pumps, gas stoves with electric ranges. And the same thing with industrial sources, trying to electrify those. It's also looking at alternatives to natural gas. So there's a lot of people looking into renewable natural gas. Manure digesters, we have a number of them in Wisconsin that generate methane that can be cleaned up and made into pipeline quality gas. Landfills, actually, Dane County has a large landfill and all their methane is compressed and put into the natural gas pipelines. And then green hydrogen is also a big area of investigation and research right now, using renewable energy to electrolyze water to create hydrogen that would go into the network infrastructure of natural gas to, again, power those industries or other sources that really need a gas for energy, and that's a possible substitute for it as well. But fugitive emission reduction is a big active area right now in the whole supply chain of natural gas, particularly in the oil, gas fields and production. And so there's a huge regulatory focus on this. There's currently a number of regulations regarding methane in the natural gas industry, but just in the last few weeks, there's been 3 more acts proposed for methane emissions research, methane super emitting strategy, and methane emissions mitigation. So lots of activity. And there's a common element in all of those, and that is methane monitoring. It's a key piece of the existing regulations and the proposed regulations. And so if you look at what those suppliers are doing for monitoring and identifying emissions, that's really important for the whole supply chain, everybody downstream, because when you talk about greenhouse gas emissions, you may be aware that their scope 1 emissions that they're in control of are our scope 3 emissions, and we need to be trying to drive our scope 3 emissions down as well. So we care what they do. And so imaging of methane sources and plumes can really aid in the reduction of methane emissions. It can identify those sources on a global scale, in quantification of the emissions, and really focus on those super emitting sources, because most of the methane fugitive emissions come from very few sources, and that's so important to identify those and understand how to mitigate that. And it complements other sources of emissions data. So that's really the message that I was bringing, is the importance of what you guys are doing for, in this case, the energy transition in response to climate change. So that's my presentation.
Thank you, Jeff. The next speaker is Eric Choi.
He's
not here.
He's joining online, so
Oh.
just give me 1 second to get him on screen. There we go.
Hi, good afternoon, everybody. Can you hear me all right?
We hear you. Thank you.
Great. I believe there's a local copy of my presentation. It might be safest to drive that. If I could please trouble somebody to advance the slides for me. I don't entirely trust myself when I sort of drive remotely. Inevitably, something weird kind of happens if it's possible to do that sort of locally.
Hopefully you're seeing it about now.
Yeah. do you
I
see
am
it?
seeing it now. Great. Thank you.
Wonderful, thank you.
Yeah. I send my regrets. I was actually planning to be down there with y'all in person, but unfortunately a few things conspired against me, so I'll have to substitute with a virtual me. And I must say, first of all, that I'm delighted to be following Jeff as the second non-academic in this session, and really I couldn't have asked for a better intro than from Jeff there just now. So thanks all. If I could advance to the first slide, please. So like Jeff, I'm here to talk about methane primarily, which is, of course, not an air quality gas per se, although I suppose it is, it's an asphyxiant. However, it is, of course, typically co-emitted with volatile organic compounds that are precursors to ground level ozone and smog. And, you know, these are phenomena that cause something like 500,000 deaths worldwide a year. And of course, methane being a very potent greenhouse gas with 80 times the global warming potential of carbon dioxide over the first 20 years, worsening climate change resulting, of course, hotter weather and more stagnant air that makes things like ozone and smog even worse. Next slide, please. So naturally, there's a long and storied history of government greenhouse gas measurement missions. One of the earliest was, of course, Skiamachi, which flew on the European GHGsat satellite for a decade between 2002 and 2012. TROPOMI, I don't think needs any introduction in this crowd, launched in 2017, measuring both greenhouse and air quality gases, have we seen, complemented, for example, by the GHGsat-2 mission of JAXA, which was launched in 2018, and the NASA OCO-3 instrument on the International Space Station beginning in 2019. And as we move ahead, we can look forward to missions like GeoCarb. So what's been very exciting, I think, over the last couple of years is that these government missions are increasingly being complemented by private sector satellites, such as those of GHGsat. And I want to emphasize that very strongly, that these are entirely complementary missions and in no way supersede or replace these important government assets. And what it really does is that it brings forth sort of overall capabilities that would otherwise not be possible with either a public sector or private sector solution at home alone, rather. And I'll give one or two illustrations of that in a bit. So next slide, please. So a little bit about ourselves. Our satellites, we like to say, are kind of small and mighty. So that picture there is actually quite illustrative of what we're talking about. So these are 15 kilogram microsatellites or nanosatellites, depending on your definition. And unlike something like TROPOMI, which is a lower resolution wide field imager, ours are have a very narrow field of view, so approximately 12 by 12 kilometers, but corresponding to that, a very high spatial resolution of less than 30 meters and a low detection threshold of 100 kilograms per hour. And as you see, this capability of almost being like a methane microscope, if you will, is entirely complementary to the government systems that I just described. So next slide, please. So indeed, as perhaps the first example, we've been very fortunate to have had a very fruitful scientific collaboration with our friends at ESRON, the Netherlands Space Research Institute, since 2019, where basically they tip and cue us using measurements from TROPOMI. So TROPOMI will detect an area of elevated methane and, you know, basically give us a shout and say, hey, what's the source of this? And we can sort of deploy our GHGsat microscope, and with that 30 meter spatial resolution, really bring it down to the facility level and identify as a point source where that emission is coming from. And I think if we go to the next slide, I'll have a specific example of that tipping and queuing in action. So in retrospect, I probably should have used an energy example, perhaps one of the observations we made for ESRON in Turkmenistan, for example. But this is something that happened last year where TROPOMI detected elevated methane over Spain. And through the course of a series of observations in August to October of last year, we identified it down to 2 landfills that were outside the capital of Madrid. These were about 6 kilometers apart, and I believe that the nearest site was just short of 18 kilometers from downtown Madrid. And these were large sources. So these were on the order of 5,000 kilograms an hour. And maybe to put that back into sort of the energy perspective, you could probably heat something like 350,000 homes if that gas were actually to have been recaptured and used in that manner. If I go to the next slide, please. This was very big news, of course, the terrible incident with the sabotage of the Nord Stream pipelines. But as bad as this was, perhaps one of the good sides of this is that it really again showed the synergy between government and private sector satellites. Literally, this sort of international fleet of government and commercial assets looking down on this particular phenomenon. So, as an example, this was observed in high-resolution optical by the Pleiades NEO satellites of Airbus. It was looked at by the satellites of Planet. The sea surface disturbances were characterized by Sentinel-2 and Landsat 8, and this was also looked at in synthetic aperture radar by Sentinel-1 and the commercial ICEYE constellation. On the greenhouse gas side, so I believe this was sort of first widely reported in the media around September 26th. We tried to task our satellites immediately on the 27th, but were hindered by cloud cover, as were many of the other optical satellites. We operate in the shortwave infrared, and but we finally got a plume measurement on the 30th of September. So there were these two here. The one on the left clocked in at 79 tons an hour. Unfortunately, I'm missing a scale there, but the length of the plume is actually 12 kilometers, quite impressive in a sort of a terrible way. The one on the right was observed a few hours later by a different satellite, actually the C4 satellite, which we launched in May. And this clocked in at 29 metric tons per hour. These were among the largest methane emissions we've ever observed. There were some third-party estimates that if we sort of wind the clock back, they were clocking, or they were estimating, emissions on the order of 1,000 tons per hour at the start of this phenomenon, based on estimating the gas pressure and the known pipeline dimensions of this particular asset. So go to the next slide, please. I think I'm just about done. In terms of availability of our data to the scientific community, I'm very happy to announce that as of 2 weeks ago, we're now under a contract with NASA to be evaluated under the Commercial Smallsat Data Acquisition Program. Perhaps some people in the audience here may have submitted proposals to be part of the evaluation team for this. I thank you for that, and we look forward to that evaluation process and to having our data more widely available to the scientific community. As it is currently with the European Space Agency through the third-party missions program, we've had our data available to European Earth science researchers for a little while through ESA TPM. And maybe I think I have one more slide, I believe. Yeah, so ultimately, this is what we as an organization are most proud of, which is the proof in the pudding of what we're actually able to do. So we've looked at something like 100,000 sites over 47 countries on every continent except Antarctica. Those penguins down there are pretty clean, I suppose. And we've got 6 satellites up there now, but just based on the 3 satellites we had last year, we detected 143 million metric tons of CO2 equivalent, which led to the mitigation of almost 2.3 million metric tons. And that's something like 500,000 cars taken off the road for years. So this is, this is why we come to work every day, and it's something that we're tremendously proud of. And with that, I thank you so much for this opportunity to speak remotely. Wish I was there, but happy to take questions at the end.
Do hold on for the panel at the end. Thank you. And our last speaker is Vikram Ravi from NREL.
Oh, yep, sorry, get my way there.
Thank you, everyone, for this opportunity for me to present here. Before I jump into the presentation, I've heard from a lot of people like you are at a renewable energy lab. What are you doing here, right? So at NREL, we do a lot of analysis, obviously on renewable energy and how that transition can happen and can happen sooner than otherwise. We do a lot of analysis of those several different studies that NREL conducts to basically assess the co-benefits and essentially to convince the stakeholders like, okay, this is additional benefit that one can get in addition to like transitioning to renewable energy that would lower the costs and all of that. So today I'm going to talk about renewable electricity adoption in Southeast Asia and the related health benefits from that. This is a large collaborative work with folks at University of Minnesota and the ASEAN Center for Energy, which is a local regional center located in Indonesia and has representation from all of the 10 ASEAN countries. So air pollution in Southeast Asia happens to be one of the most highly impacted regions, and there is a ton of sources that are impacting air quality as expected almost everywhere. Some of the sources are getting cleaner in other parts of the world, but Southeast Asia is still growing a lot. There is still a lot of dependence on, say, coal sources, and that's kind of driving the air quality impacts here. So this bar chart here on the right shows what's the attributable mortality to different sources. And as you can see, residential and commercial buildings are a large source, and then there is also energy sector, which is in yellow bar, that accounts for almost 10% of mortality in the region. And that 10% is even higher than transportation in the region. And given that this is an energy hungry region, they are growing a lot, and we wanted to study what kind of that transition what kind of impacts that transition would have on health and air quality. So we started with these 4 scenarios that are given at the bottom. So the base case is uses the existing power development plan, which is the PDP. The optimum RE scenario is it optimizes for variable renewable energy and other conventional generation is expanded. APAC RE target, which is the ASEAN RE target, assumes a fixed penetration of renewable energy. And then high variable renewable energy is the scenario that uses like a very high level of renewable adoption in the region. And then recently they as in the ASEAN region started working on updating their power development plan. So essentially to reduce the reliance on coal. So we studied the first 4 of these here. The bar charts on top right show the power generation going from 2025 to 2040. So they here we looked at 3 different years, and as you can see, the region-wide power generation goes up significantly from 2025 at almost 1,500. Goes all the way up to 3,000. Okay, I think I'm missing the x-axis label on the top there. So the one on the left is base, and then on the rightmost is the high renewable energy. And as you can see, So as you can see here, the renewable sources increase significantly, but so does coal. So coal, which is shown in blue here, coal increases significantly going from 2025 to 2040. So this is across the entire region. And on the right, on the bottom, you can see what is the fraction of these different sources. in the base scenario, we have coal at about 50% in 2025, 60% contribution from coal in 2040. In the high RE scenario, this is again still really high. So as you can expect, like when we are burning a lot of coal, that means a lot of emissions, and obviously that would have consequences, right? So in general, the generation grows almost, it doubles from 2025 to 2040, and coal generation share grows even large. So on the right, this graphic you can see, which is the emission inventory that we created and how that compares to the base scenario. So we have a base scenario, which is what ASEAN countries are expecting for now. And then for in each individual year, how different scenarios compare to the base scenario. Some of the scenarios have almost similar emissions. Optimum RE, which is optimizing for RE, but based on economics, even ends up increasing some of the emissions. In other scenarios, some of the emissions here only shown for NOx, they go up, going from 2025 to 2040. High RE is the only scenario which consistently shows a decrease in the emissions. And with that as input to the model, so in this case, we use global INMAP, which is a reduced complexity model, and add a mortality calculation module to that, and which is used here. So what I show on this is the resulting changes in premature mortality from that. Before I jump to this, I would want to tell that this is only 2040. So if we were to consider from 2025 to 2030 and to 2040, because coal is going up, other fossil fuel sources are going up, and mortality in general increases across all the years. Now, there could be some differences from one country to another, but in general, region-wide, there is a significant increase in the mortality. So this graphic here just shows for 2040 how these different scenarios compare to the base scenario. And you can see mortality in optimum RE scenario decreases by 3,000 or 4,000. There are some countries which where it even ends up increasing, despite that significant increase in renewable energy. In ASEAN RE target, again, there are countries where the mortality increases, but there are countries where it decreases. High RE target is the only scenario where mortality decreases across all the countries, and in general accounts for almost 16,000 fewer deaths in 2040. So in general, this kind of gives a guideline to the stakeholders there, to the governments, and helps them to decide like what they can do, what particular scenarios they can follow. As it turns out, some of the scenarios that also yield highest benefits in terms of reducing mortality also have lower economic cost when thinking about next 20 years or so, which is the horizon that the ASEAN countries are studying for their power development plan. So this kind of gives us an idea to them, okay, which direction we should go and which particular scenarios we can take. So this was all talking about impacts of emissions from energy generation. In next couple of slides, I'm briefly going to talk about what kind of other emissions energy interaction exists and what they mean. So here, what I'm showing is the impact of pollution on PV generation. So this is not our work, but we are doing a similar work at this point, more focused on wildfires. On the top panel here shows the PM2.5 concentration for different cities located across the globe. This shows the global tilted irradiance, which is essentially how much energy PV panels can generate. So, and then this is the relative loss that can be attributed to PM2.5 pollution. So basically that thick layer of aerosol particles is inhibiting the solar radiations to reach the ground and what kind of impact that has. And as you can see, some of the most polluted areas, for example, Delhi had a PM2.5 average concentration of 118 micrograms per cubic meter. And that results in almost 12% loss in what could have otherwise been generated by those PV panels. Even in LA, the loss is about 2%. So when we think about all of the costs associated with the energy generation, you can think, okay, 2% otherwise doesn't seem to be so large, right? But when we think of it in terms of the investment that goes in there and how much over a period of time we end up not generating, that sums up substantially. So what we are looking at is the impact of wildfires on solar generation. Here, what I'm showing is this data from Energy Information Administration. And as you can see on the y-axis, this is the PM2.5 concentration in CAISO region. And wildfire starts, this dips up from 125 micrograms. That's gigawatt hours. So when the system-wide generation was 125 gigawatt hours early on, it decreases substantially, almost to like 60 or so gigawatt hour. And here it goes even further down to almost like 50 gigawatt hours. So that is a huge decrement in the gigawatt hours that are generated. And as you can directly correlate this to the PM2.5 concentration, high PM2.5 concentration, highest concentrations were observed in first week of August. And that's when we see maximum decrease in the energy generation. So we are working on this project essentially to provide guidance to different stakeholders. So that's my last slide.
Thank you very much. What I'd like to do, you can just, yeah, flying away. You can just stay up here, and I'd like to have all the other speakers come on up as well. Sure. We'll actually start with an online question.
Okay, this is a question for Monica. Someone in the chat is wondering, is winter a good season to make these comparisons?
The NO2 lifetime is longer in the wintertime, and there's definitely more heating need in the wintertime. I don't think we'd see building heating in a different season so much. So yes.
And I'll actually just add, did you take into account the NO2 lifetime?
No, this is just straight heating degree data in TROPOMI.
Other questions? And actually, I'll just go to Eric since you're online. You told us what sort of the future of some of the governmental satellites. What is the future that in the private sector in terms of exciting sort of developments that will be potentially impacting our community?
Well, I think there's a lot of exciting stuff going on. Maybe I'll start with our plans. So we've got 6 satellites up there now. The next 6 are under contract. They're under build for launch in middle, 3 in mid, and then 3 in late 2023. And on the greenhouse gas side, we're going to be joined by other exciting assets. So there's, of course, Methane Sat from the Environmental Defense Fund, which is a mid-resolution a methane imager, which will be highly complementary again to our capabilities. And then in a few years' time, we look forward to satellites by Carbon Mapper, which will in many ways, replicate, what we do. So it's all, very exciting times ahead, I think.
I have a question for 2 of you. For Vikram, one is, I was so saddened to see the increase in coal combustion in East Asia. I want to know why. And for Monica, regarding the mapping, what about the difference in heating sources? Oil for heating versus natural gas versus other. Was that taken into account, or why? I would expect there'd be differences in the emissions.
Okay, maybe I can go first. So a lot of it is driven by economics and some of the plans that they have already put in place. I mean, in last 3 or 4 years, we have obviously seen a lot of push on renewable, right? But they had already started planning on building some of the very large thermal power plants. And when kind of, I guess, like investment decisions have already been made, they have their power plants considered all of those existing old plants, so coal plants. Now, I briefly alluded to an update to their power development plans, and now obviously the scale, economies of scale are driving renewables to be cheaper. Now, within those power development plans, they are considering more renewable sources. Now, one interesting thing that we found was when there was an increase in renewable, that was happening at the cost of something else, not coal. So now I guess I do not yet have access to or seen their new power development plans, but it would depend on what that is displacing with. So coal is like a base operating power plant, right? Now that's easier to run than, let's say, a peaker plant, which is much more costlier to run. So I think to a large extent, it is the economics which is driving all of that.
And to answer about oil heating, no, I did not look into that. That is something that we could expand to. I don't know much about those emissions. So those are not included.
Well, thank you all for your talks. It was really, really an exciting session. And actually, in my own career, I have my HAQAST side of my life, but I also chair our cross-campus energy program, and I was hired here in energy. And as Jeff mentioned, I work with a variety of energy partners. And so I've been thinking a lot about the potential for satellite data to support energy applications. And in fact, just 2 weeks ago, we had another national NASA-sponsored meeting here at Wisconsin on satellite applications to energy analysis and policy. And I just have been thinking a lot about, what an energy partnership around satellite applications might look like, and how it could be similar or different than HAQAST. And one of the big issues that's been in my mind is that, with HAQAST, health and air quality, our main stakeholder partners are public sector, air quality agencies, health agencies. But in energy, there's a tremendous engagement of the private sector. And in fact, even the public sector organizations like the DOE are very much in service to and working with private companies. And so I guess I'm curious, sort of for all of you on the panel, if you were to think about what are the data needs of energy stakeholders that could be better served by satellite data, or research needs that could bridge these gaps, like what would that look like? And I think that really this has been a beautiful panel because it's hit on methane, which is a huge connection point, energy use with Dan's talk from all fossil fuel combustion, energy use from specific sectors, and in fact, with our partner for HAQAST, the Rocky Mountain Institute, from Monica's talk, and Vikram, with your talk, really thinking about it both from the idea of the impacts of energy transitions and the impact of atmospheric conditions on the energy sector. So I guess I'm curious, where do you see opportunities for better partnerships?
I guess I could start from my perspective. I kind of alluded to that in my presentation, that obviously methane monitoring is a huge piece of driving emissions out of the natural gas industry, and particularly fugitive emissions. And just in my company, which is probably very similar to other power companies that distribute natural gas, you kind of think of the emissions from the customers. Those are CO2 emissions that, from burning that natural gas that gets distributed. If you look upstream of our distribution system, there's fugitive methane emissions, and someone mentioned earlier that methane emissions are much more potent, obviously, than CO2. It's like 24, 26 times the global warming potential of CO2. So the CO2 equivalent is fairly high. So if you look at it from a CO2 equivalent point of view, in our company, our customer emissions which are, again, our scope 3 emissions. It's not something that we're necessarily in control of, but we care about. Those are fairly high. And if you look at the fugitive emissions from upstream, from the wellhead to our distribution system, they're actually on the same order of magnitude. And when you look at CO2 equivalents, and they are a little bit less, but it's not like 10 times less. They're similar orders of magnitude. So there's a lot of fugitive emissions in the natural gas industry, and you can make a huge impact by identifying those and doing something about them. And even in our distribution system, we have ways of estimating emissions and looking for leaks and detecting leaks and going after those leaks. And the strategy throughout the industry is always to go after those super emitters, so the bigger sources. If you could identify those sources, it's the 80-20 rule, right? 20% of the sources emit 80%, and maybe it's even more exaggerated than that. So monitoring has been evolving, and it hasn't been used a lot, like a decade ago, from my understanding. And so it has been becoming more and more important, and they're getting more and more results. And so I think it enhances the satellite imagery, enhances the on the ground type monitoring. And if there were ways to complement that and to coordinate that, you could again look from the wellhead to the burner tip and understand where those emissions are, and be more effective at reducing those emissions.
I can go. Actually, I'm actually really interested in what Eric is gonna have to say to this, but I'll give an example, one of which I heard last week about methane, and Eric talked about this a little bit, but satellite data such as TROPOMI, I think is very high spatial resolution, but it really is fairly coarse spatial resolution, 5 kilometers by 5 kilometers. But then you have things like GHGsat, which are on the order of meters spatial resolution. I think that's going to be kind of the, so you could use TROPOMI at 5 by 5 kilometers to try and get a good idea of where the neighborhoods are higher, either methane or NO2, but then you can use these very high spatial resolution imagers to then really get in at the source. And what I think, again, Eric, maybe I'm speaking for you, but I'm really interested in what you're going to say, is that GHGsat is really targeted at specific locations. They can't do this very high spatial resolution everywhere. So I think using satellite data, the current satellite instruments, to get a general idea of where there's high emissions, and then these very high spatial resolutions to really narrow in on individual sources. And I think that's really a different paradigm shift than what we are doing right now, which is more regulatory, trying to generally understand sections of cities, whereas now we can potentially start looking at individual sources, individual power plants, or individual smaller sources within cities, and really trying to target those with some of these very high spatial resolution but very narrow imagers. I think Maya is kind of an example of something like that, but I know that there's other nitrogen dioxide instruments in the plan. I think CHAPS is one of them. NitroSat is another. There's all these test bed satellite instruments that I think are in the plans to be developed. And I think I'm really excited about those very high spatial resolution imagers.
Yeah, the big part of my presentation was about complementarity, and I was talking about government and private solutions, but there's also a complementarity, I think, of instruments and capabilities and technologies as well. And it's important that there's no one solution to this. We don't have the solution, but by ourselves. So what I think this really calls for is a tiered system of systems approach, where we have the government wide field imagers like TROPOMI and soon to be some of these philanthropic missions like MethaneSat, looking at wider areas and identifying where there are elevated areas of methane, for example. And then, you would deploy satellites, such as ours or the future Carbon Mapper satellites to, basically monitor these on a fairly regular basis. Jeff talked about the long tail distribution of these types of emissions in the energy sector, where there's really a very small number of emitters by number putting out a very high volume of emissions. So you can picture these satellites, looking at this on a fairly frequent basis, perhaps monitoring and detecting these biggest emissions quickly. Let's say the first 50% of methane leaked by volume. Based on those results, you can strategically then deploy, for example, aircraft or UAV sensors, and you'd put them out, say, on a biannual or quarterly basis to survey those areas, with an emphasis on any high risk areas that have been identified by the satellite surveys. And this would characterize, say, the next 40% of methane emissions by volume. And then, going down to the lowest tier, then you deploy, your ground teams and the ground sensors. So some kind of, say, occasional OGI survey, maybe a few times a year or twice a year to detect the remaining and ultimately to mitigate the highest 10% of these methane emissions by volume. So no one solution here, I think, but a really sort of integrated and synergistic system of systems approach.
I'm such a modeler. It's hard to get out of my modeling headspace. I love your question though. The way I see all these working together is, the better we can characterize emissions, the more people like me and Alex can play with what if scenarios and maybe inform, more conversations with energy sector people and find out what they need and what policies they might want us to explore, maybe.
Yeah, I guess there have been a lot of advances in, say, geostationary technology, right? So that we can, they are still far out, so resolution still remains a question. But when thinking about, let's say, the impact on solar generation, for example, where the fires actually are, how large they are, that is critical for even simulating where the downstream impacts will be. So that can provide, like, let's say, even if we assume make the assumptions on persistence, we can think of like, okay, a plume emitted here will probably end up over LA, and this is the kind of impact that we can see. So that's one aspect. Second, so that's the direct impacts related aspect. Then there is also this impact from all those soot particles deposition onto the PV panels, right? So that's another where I think essentially getting the locations of fires and size and all of those, right, is important. Third is somewhat related to what you presented, Monica, I think. So we last year completed the study called LA 100, where we assessed several different scenarios of how the city's electric grid can actually move to renewable electricity generation. And one aspect of that was looking at building and residential and commercial building sector, and somewhat related to heating. So those are again probabilistic models that are used, agent-based models that are applied there. And getting the emissions correct is basically the first step in estimating the co-benefits correctly. And that's where I think some of the things that you presented and the high resolution data, even like a 12 kilometer by 12 kilometer, if we were to grid LA by that size, that would be just a few grid cells, right? So improving those emissions is another way in which satellite data can be applied.
Oh, it's time. Oh, I'm told it's time. So I think with that, I'd like to thank our speakers and for a wonderful session. Thank you.